Okay, let's get started. If you haven't picked up your midterm 2 yet, I hope you do pick it up. They're up here. Sorry they're not in alphabetical order. I didn't have time because of the door issue. But hopefully the door issue should be resolved and some people should be coming up. Okay, so here I put the distribution up. It was actually around 5 points on average higher than midterm 1, so that was good. Yeah, I have the distribution for all the questions, and those were good too. Apart from Q3, but it's not too bad, but it's not great. Yeah, so I put the changes in the scores from the first test to the second one. A lot of people did a lot better, and some people did kind of worse, but not horribly worse, which was nice. And then I also did the sum of your individual midterm 1 and midterm 2 combined to see where you are in the pack, essentially. Any questions about the score distribution? We'll go through the solutions in a bit. Anything about the actual distribution? Okay, so let's do the solutions, or at least just go through them. So I just posted these. So let's go down to question 1. The vast majority of people on this question did it well. I was happy about that. And by well, I mean did the actual conversion fine. So actually CNF conversion is probably the easiest or most accessible thing to people who take this class. The issue that a lot of people had with this one was not following the directions where it says explain why we should do these, why these could be done. So that was worth half of the question, and then the other half was, of course, doing the conversion. The other thing that people missed was the second sentence in the directions, which is B is the start variable. So a lot of people just went on autopilot and just said S is the start variable because that's what we did in class. I put B as the start variable to make you think it doesn't have to be S every time. Just because it's called S, it doesn't have to be the start variable. So, yeah. So step 1, quite a few people missed, but all 4 other steps were done basically very well by everyone. So some people had some hit or miss things here, but basically everyone did 2 through 5 just fine. Any questions about question 1 about CNF conversion? Because there's more meaty things to get to. Okay, so let's do Q2. So Q2 was basically just an application of the regular language closure properties, just translated over to context-free, and to figure out whether or not they still hold. So for the first 3, it's wrong to say that these are the regular operations, therefore CFLs are closed under them, because CFLs are regular languages. What's wrong with that last bit? Right, there are CFLs that are not regular. So if you think that context-free languages are regular languages, you probably need to revisit that part. Okay? Yeah, okay. So the way to show these was to either proceed via a context-free grammar route or a PDA route. So I did a CFG route because it's easier and it was quicker to write down, but you could do a PDA for all of them. So for the CFG version, what you do is you just take the original start variables of the 2 grammars you have, and then you make a new start variable that goes to either the first one or the second one. There's details to account for here, but they're mostly minor. The detail there is if the 2 grammars have any variables in common, we don't want that to happen. So what you can do is enforce that the 2 grammars have different variables. So there's nothing in common between them. For concatenation, it's the same idea. make a new start variable, which goes to the first one, followed by the second one after, because that's just concatenation. And then star, we have to have s go to empty, because empty is in the star of any language. And then what you can do is have the original start variable followed by any number of applications, again, which is just going back to that same start variable that you just made. So, but the other way that you could have gone is with PDA. So for the union one, what you do is you do same thing like an NFA. You make a new start state, and you have triple epsilons to the original start states of the PDAs. But for concatenation and star, these are a little harder. So for those, what you need to do is, well, you can't just connect the old final states to the new start state via triple epsilon transitions, because we may have a stack that's not empty by the time we reach the final state. So what you need to do is to go to a new state where you pop off all the characters in between and then go to the start state. But there's an error in that too, because we don't have to pop the characters off. We need to be able to go to the start state if we don't have anything on the stack anyway. So it may have a possibility of accepting even though we don't want it to accept. So a solution is put on a special symbol, then go to some, when you're going to the second machine, have a state that pops off everything, and then a final transition that goes to the second machine that pops that special symbol off. And then therefore you're guaranteed to be empty. So, and then star is the same idea. But the key there is that you actually do need to pop the stack off, which is why the CFG version is easier. Yeah.
You didn't have to do you just do like how it is right there.
Yeah. So I just said that CFG is easier to do, but you could have gone the PDA route, and a lot of people did. It's just either one's okay. Yeah, because they're equivalent in power, so it doesn't matter which one you do. Just one is harder than the other. Any questions about these first three? Okay. For D, some people did this, not many. You could have just cited the other question that has the one language being a context-free language and its complement where you show it's not a context-free language. Yeah, so that would show it's not close to the complement. So you could have just cited that already. You could have cited the 0 to the n, 1 to the n, 2 to the n is not context-free, but its complement is context-free. There are many ways you could have gone. For part E, I actually introduced that example in class, which is instead of having zeros, ones, and twos having the same number, we have zeros, ones, and twos where the number of zeros and ones is the same, but you can have any number of twos. And another language where the number of ones and twos is the same, but the number of zeros can vary. And so the intersection of them is where you have the zeros and ones being the same and 1 and 2's being the same, which is zeros, ones, and twos are the same, which is not context-free. Any questions about those two? Yeah.
For E, in the book they did something similar, but like it was this L2 was NNM. Does NMM work the same as NNM for L2?
I have no idea what
sorry,
you said.
0 to the N, 1 to the M, 2 to the M. But I think in the book it was 0 to the N, 1 to the N, 2 to the M.
Oh, that's L1.
Oh, but then L1 was M.
Oh, okay. So I just flipped the order of what the CSE does. Yeah, but they're the same languages. It's just
Okay, so
named
you have
differently.
two to the M variables instead of just 2.
Yeah, so it's just the strings. L1 is just the strings where zeros and ones are the same number and twos can vary. So the M has nothing in relation to N. Yeah, I shouldn't have used N and M because it's kind of hard to say. But yeah, zeros and ones are the same for L1, and ones and twos are the same for L2. Okay. Any other questions about D and E? Okay. F, you could have actually cited the definition for this one by saying that, so a decider is the language of some Turing machine and recognizers are the language of Turing machines. And so therefore, every decidable language is recognizable because it's the language of some machine, which implies it's recognizable. You could have cited the definition, which I do here, of where you have a decider has to halt on all strings, whereas recognizer has to halt on the strings in the language. So halt on all strings is a harder thing to do than just on some of the strings. So every decidable language is recognizable for that reason. G, I was actually concerned about how many people missed this one. Just because of either by not citing an example of a set of languages L or a set of languages S, or not giving a certain operation, then. But the other thing that people did was to assume something about like a certain language being regular, or like a single language being closed under a certain operation. A single language is not closed under anything. A set of languages is. So one good example that I didn't even think of, but it's correct, is if I take a subset of a regular language, just take a subset of it, is it still regular? No. What about sigma star? Are there subsets of sigma star that are not regular? Yeah. So is there a set of languages which is closed under subsets where you can take any subset and it's still in that collection? One example is finite languages. So finite languages, if you take a subset of them, it's still finite, but regular languages aren't. So that's one example. But the most common one that people picked was regular languages are closed under intersection, but CFLs aren't. So, or complement, or there are many other ones you could have chose. Okay. Any questions on F or G? Okay, H is basic. I wanted you to understand that this is just the PDA to CFG process, basically the first step in doing it, which is where you had some number of final states and you triple epsilon from all of them to a single new one. So that one was pretty simple. A lot of people missed, and a lot of people said just flat out, you have to do all of them. Or you can't convert a regular grammar into a context-free grammar. So isn't a regular grammar already a CFG? Yeah, because it's just a certain type of the things on the right side, whereas CFG can have anything. So it's already a CFG. But a lot of people actually said that a regular grammar can't have unit rules on the right side. Is that true? What's a unit rule? A variable makes what? One variable and that only. Can a regular grammar not do that? Yeah, it can. So what is the thing that you don't have to do with a regular grammar, which is the right-hand side, if you revisit the definition, has only at most 2 things on the right side. So you'll never have at least 3 variables on the right side because you never make a right-hand side that's longer than the original rule. If we did, then we might have to do all 5 steps. But every right-hand side is going to either stay the same or get shorter. So we never have to do step 5 for a regular grammar. And J, I think only like 1 or 2 people got. So this is probably the most concerning one of the entire test. So consider a Turing machine that never halts on a string. Let me ask you this. What is its language? If it never accepts anything, what is its language? The empty set. What is the empty set? It's regular. So I wanted you on this question to think about what is the language of that machine. If it never halts on anything, then it never accepts anything. Therefore, its language is empty because its language is defined to be the set of strings it accepts. Okay? So that's what I wanted you to see there.
Any questions on these last three? Yeah.
It's not the final. You said you weren't going to directly ask true or false, correct? Or break something true or false on the final?
I won't do that. Yeah, and I'll actually talk about the structure of the final right after this. Yeah.
Sorry.
So the questions, it won't be true or false, but it will say like prove that.
Yeah, because yeah. Other questions about these last three? Yeah.
What if we give the language as empty string instead of empty set?
Well, it doesn't accept the empty string, so therefore it's not the right language. Other questions? Okay. So question 3, part A, this was mainly to get you to be able to do part B a little easier, although you weren't required to use part A. It was just there as a helpful guide. So the key here is that because it's finite, therefore it's regular, which implies it's context-free, and CFLs are closed under union, so therefore it's a context-free language. Another way you could have gone is, and some people did this, was, well, you can just have the start variable make each one of the finite strings, and then because you're only adding finitely many rules, you're okay. Yeah.
You post the solutions.
Yeah, I just did. Yeah, so what you would do here is you're only adding a finite number of rules. If you just have the start variable make the strings that you want directly, you're only adding finitely many rules, so you're okay there. That's another way you could have gone. So part B, what I wanted you to see here is that not to just go on autopilot for these questions. Because if you just go on autopilot, and then you may not get a correct proof off of that. So the thing that the vast majority of people missed was not picking a string that's long enough. So I said that n is at least 20 here. So people just picked 0 to the p, 1 to the 2p, 2 to the 3p, and that was fine. But the issue is that p needs to be at least 20, right? So what people did was you could pick 0 to the 20p, 1 to the 40, 2 to the 60p. That would work fine. Another way you could have gone is 0 to the p plus 20, 1 to the 2p plus 20, actually 40, 2 to the 3p plus 60. That's another way you could have gone. But the way I did it was I wanted you to use part A. So what I did was I'm going to prove that it's not a context-free language for when it's at least 0. And then I'll translate the result over to 20. So basically this proof right here is just for at least 0. And then, so here's my reasoning down here. So the one for at least 0 is not a CFL. Yeah, it's not the same as the language that I asked you to prove is not context-free. But consider this. But we know that if we take the language we want to prove not context-free, the at least 20 guy, and add in all of the extra strings, the ones that are of length at most 19, where n is at most 19, then I recovered the language that I just proved was not context-free. But consider this. Well, if L1 were the language we want to prove not context-free, suppose it is context-free, then the at most 19 one, that guy is finite. But by part A, if we have a context-free language union of finite guy, therefore we have a CFL. But the thing on the left side is not a context-free language because I just proved it. So therefore L1, the thing that we want to prove not context-free, really isn't context-free. But there are, of course, other ways you could have gone. So one of the main things that people missed was picking a string that was too short, and for the cases, either not handling all decompositions or not giving any reasoning for it. So you give all of the right decompositions, but you don't say why you leave the language. So if you just say, oh, if we pump up, we leave the language, that's not helpful to understand. It's helpful if we have all of the same character, then the proportions will be wrong. But if we have two different characters, well, the proportions will be wrong too. But in addition, we'll introduce a substring that we don't want in there. So either we'll introduce a 1, 0 or a 2, 1. Okay, but I'm pretty sure we did a very similar example in class. Did we? Okay, yeah. So the key here is that, the key here is that at least 20 thing. Any questions about this? Okay, part C, I don't think anyone got. So, and I actually have a typo. It should be the length of W is at most 119, not just 19. That was my mistake. But the proof almost is exactly the same. So let's actually go through this one. So look at the directions again. It says W is not of the form blah, or W's length is at most 19. Does that say and length at most 19? No. So is L1 bar a finite language or an infinite language? Yeah, it's infinite. So if you see this and say, oh, it's a finite language, that's a red herring. Read the actual description of the language. But even if I get the description completely wrong, think about what complement actually means here. Complement says it's not of this form right here. So it's any string, for example, that has a 1, 0 in it. Because none of the strings in here have a 1, 0. But there are infinitely many strings that have a 1, 0. And the other examples, of course. So let's go back here. Well, what I said was, let's just split this into two subproblems to make this a little easier. Let's split it into the one where it's just not of that right form, and then union it with the strings of, at most, I guess, 119. I should probably fix that. But the strings of length at most 119, that is a finite language. So the L3 language here definitely is finite and therefore is a context-free language. So if we prove that not of the form 0 to the n blah, it is a context-free language, then closure under union gets us a context-free language. So that's why I have the hint right here. What is the structure of the strings in L1 bar? Well, if it's not of the right form, then it either has a 1, 0 in it, or it has a 2, 1 in it, or the proportions are wrong somewhere. So either that the A and B condition where there are twice as many 1s as 0s is failed, or the proportion between the 0s and 2s is wrong, or the proportion between the 1s and 2s is wrong. One of those it happens. Because if we fail all of those tests, then it is 0 to the n, 1 to the 2n, 2 to the 3n. Well, if we consider, say, a regex, which is sigma star 1, 0, sigma star, that's the set of all strings that contain 1, 0 somewhere. But that's regular. And same idea with the 2, 1. So those two are regular. Well, what about the last three? Can we actually do that? So I give you a simple example, I give you an example here of the 2a not equal to b1. I'm sure you can figure out the 3a not equal to c and 3b not equal to 2c example. So how did I do this? Well, if 2a is not equal to b, then it's either bigger than b or less than b. Is that controversial? If it's not equal to something, it's bigger than it or less than it. Well, let's see. Well, if it's less than b, well, that means that there's a 0 which is matched with 2 1s at some number of times. And then at some point, there's at least one more 1 somewhere because there are more b's than twice as many 0s. So, well, that means that what I do here is that I do the a goes to 0a 1 1 to generate 1 0 with 2 1s. And then at some point, I'm going to transfer over to this variable c, which handles spitting out more 1s as the case may be. I may need more 1s, but at least one more I need. Well, In the other case, well, I match a 0 with two ones some number of times, and then at some other point, I'm going to have an extra 0 somewhere. So what I do instead here is I generate a 0 with two ones with the d variable here, and then at some point, I'm going to transfer over to the e variable, which spits out more zeros. And so the other two, the 3a not equal to c version, the only thing that you do there is you spit out, instead of 0 with two ones, you spit out a 0 with three twos. And then you handle the ones in the middle. I'm not going to handle I'm not going to consider the details here, but the idea is what is important here. Okay, so we'll think about what this is. It's the union of a regular language, and then 3 more context-free languages. So I think the entire result is a context-free language. Okay? So that's what I wanted you. You didn't have to go into all this detail, but I wanted you to actually see, okay, the complement has strings, an infinite number, where they have 1, 0, or they have 2, 1, or the proportions are wrong. I wanted you to see that at least. Any questions on part C? Okay, let's go to Q4. I think the top score on this part A was 27, so I was happy to see that some people did really well on it. But I was actually, one of the really funny things was I saw several people put empty for the set of all syntactically correct Java programs. I'm not sure if that's a jab at Java or that there are no Java programs that are correct. I thought that was pretty interesting. So let's look at them in order. So same number of 0, 1, and 1, 0. We've seen that example before, which is starts and ends with the same character. Well, we've seen that before. Well, look at the second one. W has more 0 than 1 and at most 10 zeros. So the number of ones is at most also 10. So how many strings have that form? Finitely many. Does it have a string in there at all? Yeah, 0. Yeah, but it's the most restrictive class. Yeah, it is recognizable. So so if it is finite, it is regular, and that's context-free, and that's decidable, and that's recognizable. So you are right, it is recognizable, but we want the most restrictive class. Okay, so the prime length one, we showed in class that it was not context-free. But can I show it's decidable? Can you write a program that always halts, maybe takes for a long time, to check whether a number is prime or not? Yeah, so that's, I'm sure you've done that at some point. Look at the fourth one. W does not have the same number of zeros, ones, and twos. Does not have the same number. Isn't that kind of like part C of the previous question? Yeah, so that's what I wanted you to see there. So that's context-free because it's almost the same with slight modifications to the grammar at the end. All strings with balanced curly brackets. We've done that example in class. We made a grammar for it. So for the next one, it's kind of interesting. I said in class that most compilers have a context-free grammar on the back end, but the technical correct answer here is decidable because it's not. There are some things that make it not exactly a context-free grammar, so I can't really confirm or deny that it actually is context-free. So I said that if you put decidable, that's okay too, because there's some program that always halts. If you feed it a Java program, it will always stop. The compiler will always stop at some point, but it's just, I don't know necessarily whether it's context-free. It probably is, but I accepted either answer. And if I made a mistake on any of these, just bring it to me after. So the next one, W has the same number of zeros and ones, and W has odd length. Well, if it has the same number of zeros and ones, doesn't it have to have even length? Yeah, because it's the same number. So there's no string that has that form. It must be even length and odd length. There's no string like that. W has more ones and zeros and more twos than ones. We actually did an example kind of like that in class. And we showed that it wasn't context-free, but I'm sure you can write a computer program to check whether a string really does have that form. It has more ones and zeros and more twos than ones. Just make 3 counters and check if the 1 counter beats the 0 counter and the 2 beats the 1 counter. The next one we actually did in class, which is where we have a string, £, and then the reverse string on the right side. Because they have matching characters on the ends, you just match the characters on the ends, then work your way inward until you hit the £sign in the middle. But the next one, we also showed that it wasn't context-free, and the string we picked was 0 to the p, 1 to the p, £, 0 to the p, 1 to the p. And we can definitely show that's decidable because what you do is you mark a character on the front, character on the end, next character, and zigzag your way across. Any questions about any of these? Yeah. Well, if it has the same number of zeros and ones, doesn't it have to have even length? Well, because it's an empty language because there's no strings in it. Yeah.
For the second to last one, why would maybe decidable be wrong?
Because it's not the most restrictive class.
Okay.
It is decidable. That is true. So if any of these classes was satisfied, then the supersets are also satisfied. So if I said it's regular, CFL, it is a CFL, but it's not the most restrictive class. And a lot of people actually put recognizable on some of these because I'm not sure why. We actually, at this point, didn't prove that there was a recognizable language that wasn't decidable, so none of these should have been recognizable. You had a question?
Yeah, I put finite for a set of also technically JavaScript programs.
What's that?
Why is it a CFL?
Because there are infinitely many valid Java programs. There were some people that put, I assume that this was the set of Java programs in existence. And if you put that assumption, I think that's okay. But a set of all possible Java programs that are syntactically correct, that is an infinite set. Because, for example, I can just add comments on the end of a syntactically correct program, as many as I want. So that's why it's an infinite language. CFL or decidable was fine for that one. Other questions? Okay, part B. A lot of people just went on autopilot on this one too. What is the task here? The task is not to determine whether the string on the tape is a string W, £, then a string W. So note the directions here. It says what you're tasked to do is to go to the except state with W, £, W left on the tape. Should you ever go to the reject state? No, because there is a string on the tape, and you're tasked to put a copy of it with a £, in the middle, and you're going to the except state. So you will go to the except state at some point. But, so how would you actually do this? Well, here's the thing. I have a string on the tape, and we want at the end to have string, £, then the string. Well, I can't just mark up the left side, the original string, because I need to keep it around for when I go to the except state. I need to have the original string still there. So the idea, what I wanted you to do was mark a character on the left side, then put it on the right side in the next available slot, then still remembering which character that you just did, unmark the one that you had before. So if it was a 0, for example, you put a dot on that 0 so essentially a different character. Put a 0 on the other side. Come back until you hit a 0 dot. Unmark it. So put a 0 there and then move right 1 position. So it's kind of the same as the W decider that we made, where you mark zigzag across. But I wanted you to, instead of just marking a character on the right side, I wanted you to put a character there. And on the left side, I wanted you, instead of just marking it, I wanted you to mark it, then unmark it. Okay? That's what I wanted you to do there. Questions on part B? Okay, so let's do question 5. So I didn't actually put the PDA on here because I wanted you to see a grammar instead, because you can convert this on your own time to a PDA. I just wanted you to see the grammar first. Yeah, so I just left out the details. So here's the thing. A lot of people put the grammar as S goes to 00S1. Well, the issue there is it doesn't have to be zeros and then the ones afterward. The language is a set of all strings which have this twice as many zeros as ones. They could be in any order, okay? So you don't know where the zeros and ones actually are. You just know that there's twice as many zeros as ones somewhere. Well, think about what this language is. So if there's a 1 somewhere, there are 2 zeros somewhere else that are matched with it, right? Because there's twice as many zeros as ones. And 2 spit it out through the string. Well, between the 1 and the 2 zeros, there could be anything. So it doesn't have to be 1, 0, 0 right next to each other. It could be a bunch of zeros in a row. So what you do here is you say, okay, the 1 and the 2 zeros are going to be matched at some point, but anything in the middle between them could occur. So that's why I have the S's all over the place between them. Yeah. So yeah, and I'm just handling all the possibilities where either the 1 occurs first and then the 2 zeros are after, or the first 0 comes first, then the 1, then the second 0, or the 2 zeros first and then the 1 after. So those are the only 3 possibilities. And I just put S's sprinkled throughout because anything could occur in between. And then the crucial rule, which is S goes to empty, because empty has twice as many zeros as ones. And then the 2S rule on the end is, well, I don't care where the 2's are or how many there are. So if I need to put a 2 here, I'm going to allow you to do it. So 2's can go anywhere. It's just that the 1 has to be paired with exactly 2 zeros. Okay? But to convert this to a PDA, what you do is you just make those 4 base states. And then in the looping state, you have these 4 outgoing things. 1 for each of the 4, I guess 5, I guess. For each of the 5 rules, you have these outgoing paths, and then you put them together. There is a simpler way to do it. I'll let you think about it, but this is the way that I wanted you to see. A 1 with 2 zeros that are matched with it, and anything can go in between them. Any questions on that part A? So for part B, I'm going to omit the details here because I don't have a PDA to show you. But if you made a mistake in part A, I didn't penalize you in part B. So if you made a wrong PDA before, if you just made the conversion correctly to allow the PDA to be converted to a CFG first, then I just give you full points. So what I wanted you to see here is the PDA to CFG conversion, which is we got to have a single final state. So we triple epsilon from all the other ones to that single final state. The thing that most people missed was number 2, which is for that single final state, you need the popping transitions on it, because I need to have the stack allowed to be empty at the very end. And then step 3, pretty much everyone got, which is You can't have any transition that does neither push nor pop, or you can't have a transition that does both. So people correctly just translated those into 2 transitions, which is good. Any questions on part B? Yeah, people did really well on part B. Okay, part C. Okay, yeah. So only like one person got reasonably close on this. So this is from a previous homework that I had. So I'm just gonna speak it and give you a sketch of how to do it. So what is this thing? So what it is basically you have a bunch of NFAs, but instead of just them being normal NFAs, the NFAs can actually call themselves. So look at this NFA that I have right here. Well, it's not an NFA, but it's close. The main transition from Q1 to Q2 is basically we're going to call the module, as it's called, the main module again. So if I take that transition from Q0 to Q1, then what I'm going to do is on a new stack frame, as it's called, I'm going to restart another version of that same machine. So, for example, what I can do in the allocated version is I'm going to go from Q0 to Q3, and then because there's a single final state and there's nothing left to do, I take this stack frame away, resume computation in the original machine, and at this point we're in Q2 because we're done going through the main machine before, and then I can take the one transition at the very end to Q3. And so this ASA, as it's called, recognizes 0 to the n, 1 to the n. So how do you actually show that these have the context-free languages? Well, think about what happens here. What we could do is say, ignore the S line, just the first line at the top. Well, look at the ASA itself. Well, you're starting at some place and you're ending at some other place. Doesn't that kind of look like a PDA with a single start state, single final state? Well, it's actually easier because it's an NFA. So what you do is you make a variable called main, or M, and for any path that goes from that state to the end state, I just read out what happened along the way. So in this case, I just say the M variable could make empty, which goes to the final state directly, or it can go the other route, which is generate a 0, then call ourselves, which is the M variable again, and then at the very end, generate a 1. So that's actually how we make that CFG there. So that's essentially what you do. And then the other direction is, if I have a CFG, you basically just do the process in reverse. So what you would do there is, if I have a bunch of rules on the grammar, what I do is for the ASA corresponding to that variable, I make one giant path that goes from the start state to the single final state. And that's it. So that's what I wanted you to see. Any questions on Q6?
So what would be like the right answer?
So what you would do is you would say, if you have an ASA like this, then for each of the modules, what you would say is make a variable for each one of them, and then for any path from the start variable to from the start state to the final state of that module, just concatenate the path along the way and make a single rule for each one of those. And then after that, what you would do is say, well, if I have a grammar, how do I make an ASA out of it? Well, what you do is, for each of the variables, make a module, and for each of the rules, make a giant path corresponding to that rule. So it's basically doing the same thing in reverse. So yeah, that would be a way to do it. Any other questions about Q6 or the test or anything else? Yeah. Oh, sorry? Oh, that's a loaded question.
Yes. I waited for this.
So remember, I can't promise anything because the final's going to replace this.
Wait, so you remember how you said like final's gonna replace the grade?
It'll replace it if it does better.
So are you saying like by the score it does better or
Percentage-wise.
by the average? Oh,
Yep, percentage-wise.
percentage-wise.
Yeah. So if you got so is this hard to understand?
No,
Nothing about you, but it's just like it
that is so about me.
is there can I clarify anything about that?
Yes.
Yeah, what can I
So
clarify?
let's say you got the first place. First place. You got the best score on the final, right?
Yeah.
And that's like 50 out of 250. That's not going to replace anything.
That's not going to happen.
Okay,
but
yeah, that's not going to happen. Sorry, guys.
no, you were hinting at something though.
Yeah, go on.
No, because
What are you saying?
that's what I was saying. So even if you got like really bad scores, and that score, like lower than that score, is considered like good score on the final, you're still gonna get a bad score because you did bad on the first two, right? Do you get what I'm saying?
So let's work.
Replacing your percentile is higher on the final than it replaces your percentile.
Yeah, it's lower.
But it's considered.
So let's work out a concrete example. So So think of me as taking the class.
Okay.
So what do I earn on midterm 1 out of 250?
I don't know, like 100? Yeah.
Okay, so let's do 100. What do I get on midterm 2?
Like 130. 141.
Just an
So let's
example.
say you get 120. Or 99, right?
On the final, I get a 99 points or 99%.
99 out of 250.
I think he's trying to say the 99 out of 250 would be the highest out of everyone.
The final's out of 400 points.
Oh, just kidding.
What was asking? Well, wait. So is it purely point based? Like
Purely point based.
So if
Oh,
I got
well,
200 out of
Oh,
400,
sorry. It's percentage
Yeah.
comparatively, but I replace the original point value with that percentage.
Right.
So let's make it a little easier to say. So let's do 200 for this guy and 125 for this one. So this is an 80% and this is a 50%, unless I did my math wrong. Okay, so let's just say I get a 70% on the final. Let's just say. So that would be a 280, I think. So that is a 70%. So what would happen is the midterm 2 would be replaced with 70%, which corresponds to 175. So then I would add those three. Yeah.
Then if you got 90% on it, it would replace both.
Yeah, it would replace them both with 90%. So let's work out this other scenario. So let's just say I got a 90% on this guy. Guys, so if we got a 90% on this, which is 360, then this would be replaced with 90%, and then this would also be replaced with 90%, which is, let's see.
225.
Yeah, 225. Yeah, so I do the best possible thing. Yep. So I replace them both if it does better. I replace one if it's better than one and not the other, and I replace neither if it's not better than either. Yeah. Guys.
I know a lot of material in exam 1 and 2 obviously you get from how much could you say like from exam 1 and 2?
I'm going to talk about that in just a second. Yeah.
What if the midterm score is higher than both of the midterm 1 and 5?
Then nothing happens.
Shouldn't you say like you will be replacing the score
It's-
incrementally?
I'm doing exactly what the syllabus says, which is I replace the final with the I replace the final score over the midterm scores if the final score is better than the midterm scores. No, because the final is cumulative. Yeah, so my philosophy is if you can show that you've learned the material at the end, why should I punish you earlier on? So that's my motivation.
Has anyone got above 80% on your finals?
Probably was one.
Well, considering that I'm gonna not have it be true-false based, then whereas I did before, no one ever did before, but it's not gonna be this time, so it definitely is very possible.
So it's possible.
It's very possible.
On average, how many grades are replaced?
Oh, good question. So the majority of grades that are replaced are minor. So they're not like huge bumps in grades at the very end. Last semester, I had one student who, because he did so well on the final, it raised his grade from a C to a B. So a whole letter grade change.
Wow.
But that's more the exception rather than the rule. So if you are thinking, well, I need a lot of points to do X in the class, then this is what you need to start thinking about. Okay? Any other questions about this only? Because I'm going to talk about the structure of the final in a second. What? Oh, yeah, cutoff, sorry. Yeah. So let's see. Can I actually write on this? No, I can't. So let's see. The 384 I'm going to consider. So this is just a. I can't guarantee anything. So the things can change. I try to make this as reasonable as I can. What I do is I look for natural cutoffs in the distribution, and I say that is where I'm going to put a cutoff. I'm not going to put it between like a 313 and a 312. I'm not going to put a cutoff there. That doesn't make sense. I put groups of people together. So like the 384, I'm going to say is an A+. Let's say from 349 to 319, oh no, let's do 312. I'm going to consider that A and A-. And then 293 through, let's see. It's kind of hard at this point because the scores are kind of bunched together, but I would say 293 through 269, I would consider that like B plus B, and then so on and so forth down. So I try to look for natural breaks in the data. But I also take into account how many classes have you attended? Have you gone to office hours? How many homeworks have you handed in? Like your engagement in class, because I can tell. So I don't just take raw values and I just say, oh, there's the letter grades. That's not humanistic. Okay? Any questions otherwise on cutoffs or anything like that? I can't hear you.
I wanted to know the math on
This is 1 plus 3.
Yeah, I'm just doing it for the 1 plus 2. Yeah, because that's the thing that matters more. Because the individual midterm doesn't count because the final's going to possibly replace it anyway. I just want to see like your overall what you've done so far, and also the attendance is of course going to affect your grade a little bit, so that could actually change things. So like a lot of people have really good attendance so far, so you're going to be pushed up quite a bit. So I wouldn't worry that much about that sort of thing. I would worry more about what concepts are you not getting. So if you missed points twice on very simple things, I would very much revisit those things. Okay? Understand why you missed the points. Not just, oh, Ryan's evil because he didn't give me an A right now. I'm trying to tell you, whereas other professors may not, I'm trying to tell you what you're missing and how you can actually succeed, because I want you to succeed. I don't want to fail people, but I have to do my job. Yeah.
You're still accepting questions for next Tuesday.
Yeah. So I'm still accepting questions for the review next Tuesday. When's the final? Wednesday. Good. Yeah.
Oh, I was just wondering when you're going to cut off and stop taking questions.
So I technically will stop taking questions when the Tuesday review starts. By email, I mean. Yeah. It's just that I need some time to be able to see, okay, this is what people are worried about and like they want me to go over again, so that I can give really good examples instead of just like really crummy ones that I've been making up in class as I go. So yeah.
So can we actually like request a specific example then?
Yeah, that's the whole point. Yeah. Say, okay, I didn't understand this proof of ATM, or can you do an example of Rice's theorem?
So would you prefer then like by Sunday night?
Yeah, like by
having a specific example
Yeah, by like Sunday night or Monday, yeah, something like that. Yeah.
Will you provide like a data sheet so that it's asked?
I probably will. Yeah, I'll provide a past exam. The only problem is that last year it was entirely true-false based and multiple choice based. And then the one before was partly multiple choice true-false based. So it may give you a false sense of what the actual test is because I'm going to tell you what the actual test is going to be testing on anyway. So I want that to be a fair warning before I put those up. Other questions? Okay, what thing do you want to know right now? What's the structure of the final? You want to know that? Cool, let's look. So the thing is, I want this test to be more about, instead of doing brute force work and writing a lot of things, for you to think about, okay, what has this class been about? Instead of just like, it's been a blur of information I'm never going to use again, is what is this class actually about and how it's actually useful. So the final is going to have 4 questions plus 1 bonus worth 100 points.
Oh my god.
So 100 points each plus a bonus worth 100 too.
So you can get 500 in theory.
Yeah. Mm-hmm.
In theory.
Not proven.
I'm not saying I'm gonna
Nobody's gonna prove that.
Such a great joke. I've never heard that before. Anyway, so what are the questions going to be? So what are the major topics that we covered in class? Regular languages, context-free, and Turing machines. So question 1 is going to be about regular languages. Q2 is going to be about CFLs, or I guess things related to regular languages and CFLs. And it's only going to be about those things. It's not going to be like Turing machine-based things on regular. It's really about regular languages. Q3 is going to be about Turing machines, decidability, as well as undecidability. So basically the things we've been doing. And the things that we're going to get to today and then tomorrow too. So you notice I put 4 questions here, and I only wrote 3 because there were only 3 major sections. What do you think Q4 is about? The class as a whole. So basically the entire class. So Q4 is really meant to say, let's forget about all the details for a second. What are the important things and what can we say about these 3 major things? So the Q1 through Q3 are more detail, I guess, based. And then Q4 is going to be, let's look at this from a high level perspective. And can we say anything about it as a high level thing? Okay. I think that would be a reasonable, so it really is equal representation of all subjects that we've done. Because that's how I want the final to be. Yeah.
So there are going to be like sub-questions within.
Yeah.
Language, right?
So what I'm anticipating is that each one's going to have 4 sub-questions. So, and by that I mean it's going to be 1 page front and back for each one. So 2 parts on one side, 2 parts on the other side. Or maybe 2 parts with 1 on one side, 1 on the other side. And then you'll get plenty of scratch paper, all that stuff. It's just that I don't want the test to be long because I have to take your test to the Czech Republic with me, so that I actually have to grade them. Because I have a tight window to actually grade them, and I have to grade them on the plane if I'm going to do that. Because the day after that, I'm at a conference giving a presentation. So, yeah, I have a tight window. Yeah. Oh, sorry? What would happen if I lost the test? So what I do, everyone gets 100. No. So what I always do is, like I did for your midterm 1 and midterm 2, I scan all tests first. So I just feed them through a scanner. And so I have a digital version. So I'm going to do the same thing for the final. Because I do have time for that, I don't have time for grading. So yeah, so I'll always have a copy available. Yep. Yeah.
So, like, when you're talking about high-level overview of the concepts involved, you talk about like the theory of how the subject came to be, or can you give a more concrete example?
So, like, is there any type of thing that unifies all three major topics that we talked about? So, are there things that we can say about regular languages, CFLs, and Turing machines that encompass all three of them? So, it really involves questions that talk about all three of them. I mean, I could talk about an example, but it won't appear on the test as a result if I talk about it.
Well, that's more useful because at least you can extrapolate. Like,
Yeah, but is it on the test now?
It would be.
No.
No.
Okay. Okay. What do you think? Is it easy? What do you think?
Watch some guys go up to
Yeah, so Q1 through Q3 focus more on the actual topics and actually what we actually did with them. And Q4, think about the entire class as a whole. So I'm not going to ask very specific things on Q4. I'm going to ask high-level type things. So here's one that wasn't going to be on the test, but could be an example of a Q4. Suppose that we had two different machines where we had one that's DFA-based and one of them that's C++ based. So we had one program that's based on a DFA and one that's based on C++, a programming language. So what is an advantage of using the C++ guy over the DFA one? Or in general? Yeah, not just the language itself, that doesn't matter.
Like higher level, easier to do like more.
It may be easier to work with. What's another advantage? More importantly, what's the other advantage? It runs on, the DFA one does too. What's the other advantage? Yeah, it recognizes more languages. It's because the C++ one is based on a Turing machine because of the Church-Turing thesis. So because they're equivalent in power. So because the Turing machine has more power than the DFA, the Turing machine is more useful. Why would we want the DFA version over the programming one? What's an advantage of the DFA? Well, it may not be faster, actually. Because remember, the DFA has to read through the entire input, whereas the Turing machine doesn't. What's another advantage of the DFA? It's simpler conceptually, but what's another reason? What are the languages that we've been talking about recently that are easy to do for DFAs, but impossible to do with Turing machines? What is A sub DFA compared to A sub TM? A DFA is decidable, but ATM isn't. The emptiness problem is decidable. Even more importantly, the equivalence problem is decidable for one, but not for Turing machines. So those are the types of questions that I want. Those are the things that really test, do you understand the material at least at a high level? Do you understand the relation between these core concepts and why they're important? Okay? Those are the things that I care about more. Because, I mean, who cares about like the details of some proof? What you should care about is, okay, I'm trying to do this task for my job. Can I implement it as a DFA? Because if I can, then I can guarantee some properties that are really nice. Could I parse this? How should I parse these emails that are coming into our company website? How should we do it? We probably should do it as a DFA. Or as a regex, I guess, but equivalently a DFA. So thinking about what models are right for the right problem, those are the things that I want you to think about when you come out of this class. Not like, okay, what does the I represent in the pumping lemma proof? That's not important. The important thing is understanding why these objects are important. Okay, that's what I wanted you to think about. Any questions otherwise about the final? Okay, we are way over time for a break, so let's take a break.